So waves, learning outcomes 1 to 5. Number 1 is just a simple one about the definition of what causes sound. So all sounds are caused by a vibrating object. Okay, so if you think about hitting a drum, right, plucking a guitar, or even touching your voice box when you're speaking, you feel the vibrations that are causing the sound. And for number 2, it's all about the wave shapes that we see. And we've looked at these in class, but with those wave shapes we also need some definitions. So I'm going to start with a few definitions and then move on to diagrams. So amplitude, usually abbreviated to capital A, is how tall a wave is. From middle to top, or from bottom to middle, because waves are symmetrical, they go down as much as they come up. And that would be measured then in meters or centimeters. It's an actual length. Wavelength, now the letter for wavelength is the Greek letter L, which is lambda to give it its name, but looks a bit like a giraffe. Right, so I draw that bit first usually. Right, the kind of front legs of a giraffe is how I like to think of it. And that's the Greek letter lambda. And that's how long a wave is. Now there's various ways you can measure that, but the simplest is usually, so I'll put often measured from crest to crest. But I'll show you in the diagram different ways of doing that. And then the one other definition we need isn't an actual length, so you can't see it directly in a diagram, but you can see the effect it has when it changes it. So frequency is how many waves there are each second. So when we look at these what are called oscilloscope diagrams, if there are more waves a second, then you'll see more waves on the screen. Okay, so that does therefore have an effect on the wavelength that you see in these diagrams as well. So what we're going to do is practice drawing some of these wave shapes, right? And this does take a wee bit of getting used to. And what I would strongly suggest you do is you use the lines in your jotter to help get this right, and put in some wee guide dots. So if you're doing this in your jotter, I would suggest for this first one that you come down 3 lines and then put your first dot. So you're leaving yourself a wee bit of space. And then I'm going to measure a centimetre in. Okay, so I'm going to come in a centimetre. Now I'm going to put these in as guidelines in a different colour, but then I'm going to get rid of them afterwards. So if I come in a centimetre, and then go up 2 boxes, so that was 1 centimetre. So like I say, you don't actually need to copy these, but it's just to help guide you. And then go up 2 lines. Right, I'll get rid of them in a wee second, but that's where I'm going to put my first dot. And then I'm going to come in another centimetre, but going back to the middle. It's much easier on line paper, or even easier yet on square paper. So that was, in terms of my guidelines, that's another centimetre across. And then same sort of idea, a centimetre across, but this time we're going to go 2 lines down. So my guideline comes along a centimetre, and then down 2 lines, and then I'm going to put a big blue dot there, and then you get the sort of idea. Back up, so 1 centimetre along, back to the middle, 1 centimetre along, 2 lines up, 1 centimetre along, back to the middle. 1 centimetre along, 2 lines down, and 1 centimetre along, back to the middle. Okay, so you can use the lines in your jotter to help make that nice and clear. I'm going to now score out, hopefully, these guidelines that I've done. That'll leave a space for putting in other stuff later. But what you should end up with then is a set of dots looking like that, nicely spaced. And then we're going to draw smooth curves. So these are not triangular, that's a kind of common mistake it looks. Right, we're going to draw a smooth curve, and it's much easier to do this in pencil, just in case you make a mistake and you want to go back and modify it a wee bit. So try and draw smooth curves through these dots. Now, I'm not going to penalise you, even you see I'm doing this with an Apple pencil. It's not as smooth as I would normally with a normal pencil, but I wouldn't penalise that. Okay, that would be acceptable as long as you're hitting your dots and it's a nice smooth curve. And what that ensures then is that you're maintaining a constant amplitude and a constant wavelength, which is all the ways we're going to study that's going to be the case. Okay, so on this now, I'm going to use a different colour just to define some of these words which we were using up above. Okay, so an amplitude is how tall a wave is from middle to top. So that could easily be marked in there and there. So we'll call that capital A. But it is also from bottom to middle. That's worthwhile knowing. So I could have also put an arrow in there. That's an amplitude. And what that means is from bottom to top is twice the amplitude. Right? Once from getting from bottom to middle and another from getting middle to top. So that's our amplitude. Our wavelength, now the easiest way to do that is from crest to crest, but I haven't actually defined a crest. A crest is the top of a wave. Another word that we could use that comes up occasionally is a trough, which is the bottom of a wave. And a wavelength then, the easiest way usually as you're marking it on a diagram is from the top of one crest to the top of the next. Make sure that arrow goes all the way along. It's not meant to kind of just stop in the air and point roughly towards these. It needs to go all the way exactly to the top of that, to the top of that. So that's a wavelength. I could also mark a wavelength from this starting point, but just watch this one. That's a complete wavelength as well. So I wouldn't stop at this point here where the wave comes back down, because it's not done the up and the down part of the wave. So that wouldn't be a complete wavelength. So that's the kind of points of a wave that you need to know. Right? A frequency, let's say, we'll see what effect it has when you change your frequency, but frequency isn't a physical measurement that you can actually see directly on a diagram. In this second learning outcome, we need to look at the effect, having defined all these, of what happens if you change things like the amplitude, the frequency, or the wavelength. How does that affect these diagrams? So to do that, I'm going to draw the diagrams for some different situations. So this next one is, well, what happens if I took the same wave as I draw in the first diagram, but I had a larger amplitude version of it? So larger amplitude, but same frequency, same wavelength. So I need to take the same sort of principle as I was doing in terms of drawing those dots, but for a larger amplitude I'm going to have to go up and down more. Okay, so if you're doing this in your jotter, this time I want you to come down 4 lines and put your first guide dot, and then measure 1 centimetre in, and this time go 3 lines back up. 1 centimetre in, back to the middle. 1 centimetre in, 3 lines down. So I'll just put in a wee guideline just for a wee second, just to stress. That's 3 lines up and 3 lines down. Okay. and then just continue in this pattern. So because we're not changed the wavelength or the frequency, I'm just going to keep going along 1 centimetre back to the middle. 1 centimetre, 3 lines up. 1 centimetre back to the middle. 1 centimetre, 3 lines down, and 1 centimetre back to the middle. Okay, and now I can rub out my guidelines, and I've now got my dot structure for drawing my wave. Once again, nice smooth curves. You take a wee break every now and then, get your pencil in a good position. Okay, so there's our larger amplitude now. Same frequency, same wavelength wave. Okay, so the wave has got taller. What happens if I change the frequency or the wavelength? Because if you change one, then the other will also change. So I'm going to go back to same amplitude, and this means the same as the first wave that I drew. So remember, we were 2 boxes up, 2 boxes down. I'm going to look at a smaller frequency, which means there will be less waves on the screen, right? Which means that they'll have to have a larger wavelength, right? They'll be more spread out, basically. So this one's actually a wee bit easier, right? But I'll just go along. So you need to come down 3 lines for your first guide dot. But this time, right, we're going to go 2 centimetres in. So I do my guideline again. This time it's going to be 2 centimetres in, 2 lines up. So I can now put a blue dot there. 2 centimetres in, back to the middle. 2 centimetres in, down to the bottom, 2 lines down. 2 centimetres in, back to the middle. So I only need 5 dots for this one. I'll get rid of my guidelines again. And now I can draw in my smooth wave. Okay, so that has the same amplitude as the one on the previous screen, so it goes up and down by 2 lines, 2 boxes, but it has a smaller frequency, so you only see 1 complete wave in the same time you saw 2 complete waves. There are less waves each second. Or another way of thinking about it, it's a larger wavelength. Okay, so in the previous one you had 2 complete wavelengths in the same space. Here you've only got 1 complete wavelength, so the wavelength is larger. So in this learning outcome, what we're going to do is take the physical concepts which we defined previously, frequency, wavelength, amplitude, and link them to everyday sounds. So for example, a sound wave with a larger amplitude will be louder. Okay, and the opposite would obviously be true, so a smaller amplitude would be quieter. A sound wave with a larger frequency and therefore smaller wavelength, but it does tend to be frequency we talk about, will be higher pitched or a higher note. Okay, so if you're playing a musical instrument, as the notes get higher, basically what you're doing is producing sound waves with a higher frequency. So that links that concept to the more everyday terms. Now we're thinking of the idea of what frequencies you can hear. We measured that in class. Most humans can hear frequencies. So at the bottom end it tends to be 20 hertz. And at the top end it's not so well defined. Even at the bottom end it's not a dead exactly 20 hertz. But it's roughly 20,000 hertz at the top end. And as we looked at in class, that's different for different people, different ages. As you get older, that top end tends to decrease a wee bit as well. But the accepted range for frequencies is from 20 hertz to 20,000 hertz. And sound waves with a frequency greater than 20,000 hertz are called ultrasound. So these sound waves still exist, but it's just that our ears can't pick them up. Now some animals can, for instance, so dog whistles are based on that sort of principle as well. Okay, but that's our definition of what we call ultrasound. So it's not that the sound is fundamentally different, it's just that your ears can't detect it.